Hello, welcome back. College Algebra. This video is for you. Um, so the last section that we did was section 7-5. If you remember, we did 7-1, 7-2, 7-3, skipped 7-4. Okay, we're not doing partial fractions. Went to 7-5. Okay, talked about matrices. Now, believe it or not, what we are doing is we're going to section 8-1. As far as a chapter 7 test goes, since everybody's at home anyway, I mean, a test is really just another assignment. So I will put one on there for you, but you can, have, I mean, it's not going to be timed or anything. I mean, I can't really proctor it. So you guys can just do it for some extra practice. 7-6, by the way, which has to do with solving larger matrices, or using larger matrices to solve equations. We're not going to do that either. What I'm going to try to do for us is get through all the material that I know absolutely has to be covered because it's always on the final. Then if we have some time at the end, we'll go back and hit the topics maybe that we didn't cover just in linear order. So this is 8-1, and the topic for 8-1 is ellipses. So we're going to start very basic here and talk about what is an ellipse. Eliza, do you know what an ellipse is? Okay, Eliza in the background is making a shape with her hands that actually does look kind of like an ellipse. An ellipse, you may think of it as an oval, okay? That's a word that's often used colloquially, but in math we call a shape that looks maybe something like this, we call it an ellipse, okay? It's like if you took a circle and mashed it a little bit, okay? I mean, that's not really what it is, but it kind of looks like that, okay? So an ellipse. Now, where do you see ellipses in real life? All over the place, really. Eliza, can you think of some place where you see ellipses?
Well, like whenever, when planets travel around the sun, they travel in the ellipse.
That's very true. Yeah, and all our planets travel in elliptical orbits. I'm going to use a term here. The eccentricity of those orbits is very low for planets. So the orbits are almost round, but they are definitely elliptical. And some orbital bodies, like comets, have elliptical orbits that are extremely eccentric. I don't want to describe all of that right now until we kind of know what the structure of an ellipse looks like. But we will. We'll look at some planetary orbital structure. Okay, now this chapter, all I've said so far is what is section 8-1 about. Chapter 8 is about a topic called conic sections. Okay, and what is a conic section? Well, there are 4 of them. Okay, and they are all two-dimensional shapes, like an ellipse is a two-dimensional shape. Another one is a circle, okay, which is, I'm sure everybody's familiar with what a circle looks like. Then another one is a parabola. Again, I'm sure that everybody knows what a parabola looks like. And then finally a hyperbola, which you may or may not know what that looks like, but you will. But the first one we're going to do is called an ellipse. Now, why are these 4 different two-dimensional shapes called conic sections? Well, here's why. I want you to envision, you've all been to Dairy Queen before, I'm sure, right? And you've gotten an ice cream cone, Eliza?
No.
Okay.
No, I get Blizzard.
Yeah, okay.
It's better.
What I'm going to do is I'm going to draw an ice cream cone. Okay, not the crap kind of cone with a flat bottom that tastes like cardboard, but one of the good kind of cones that's an actual cone and tastes, I guess, kind of decent. But so we have an ice cream cone here. Excuse me, right side up. Now I'm going to balance this ice cream cone on top of an identical ice cream cone that's placed upside down on a table. Okay, so I have one ice cream cone balanced on top of another ice cream cone. That is called a double inverted cone. The reason the four graphs, circle, ellipse, hyperbola, parabola, the reason that those four two-dimensional shapes are called conic sections is because they can all be obtained by slicing a double inverted cone with a plane. Now, the easiest way to think about this is as follows. Take a piece of paper, okay, a stiff piece of paper, and stick it through the top cone exactly horizontally. Then look down from above, and the set of points that make up where the cone intersects the plane, what does that look like?
A circle.
It does, yeah, you're right. Yeah, if you slice this horizontally, the locus of points where the cone intersects the plane is going to be a circle. That's good. That's a conic section. Now, what if instead of slicing the cone directly horizontally with the paper, we tilt it a little bit so it slices like this? Now look down, and what is the set of points going to look like?
An ellipse.
An ellipse. Very good, very good, very good. Now, Eliza's not going to know the answer to this next one.
Oh, dang.
Well, we'll see. We'll see. Let's say I
will.
take the plane, and instead of slicing it at an angle like that, I make it to where it comes out the top of the cone. Okay, I do it like vertically. Now, the set of points where the cone intersects the plane. Can you picture it, Eliza?
I don't know what you're saying.
Okay, so
I don't think you're
I'm going to
describing
slice.
it well.
I'm going to slice this cone with a plane going straight down like that. Okay, so she just drew something in the air that looked something like that. Is that kind of what you want to do? Yeah, and those of you viewing at home who are a little bit smarter than my daughter.
Oh, thanks.
That's called a parabola.
I know that.
Oh, okay. Well, why didn't you say so? All right, and then the one that maybe none of us know just yet is if I take that plane and I slice it all the way down through both cones, okay, like straight down through here. Okay, can you tell what you'll get?
It's called the hyperbola.
Hey, process of elimination. There you go. But you get something up here, and then you've got another slice down here, and that's not a very good hyperbola. But a hyperbola does have two branches, and of course we're not going to talk about a hyperbola today, or anything else except an ellipse. How about that? So that's just an explanation of why the two-dimensional shapes that we talk about in this section are called conic sections. So what I hope to get accomplished in this first video is to draw a picture of an ellipse that has all of the parts, okay, all of the features of an ellipse on it. Now, when I do this at school, I've got like this giant, 4x8 whiteboard, and I've got plenty of space. We'll try our best here to not make this get too cluttered. But here's how we have to start. I'm going to start, and you can maybe try to recreate this at home. But I'm starting with just an XY coordinate plane, and I'm not going to put any tick marks on it. And although I don't have to, I'm going to draw this ellipse entirely in quadrant 1, just so it looks neater. Okay. Pardon me. Okay. So here's what I'm going to do. I'm going to start by just actually physically drawing an ellipse there. Okay, so where I drew an ellipse, and I mean, it's not a perfect ellipse or anything. I can explain to you how to draw a perfect ellipse. I think, Eliza, you know how already. Didn't I do that with you one time? With the string or something?
Yeah.
Okay, yeah. Okay, now here, let's go. So this is the actual ellipse. Okay, that's a shape. You may have called it an oval when you were children, but now that we're all adults, we'll call it an ellipse. And right in the middle, you can probably guess what this point is called. Starts with a C, Eliza.
Center.
Center. Perfect. Okay. So this is the center. Now, the coordinates of the center. The center is a point, all right, and it's on a x-y coordinate plane, so it's going to have an x and a y coordinate. And we call those coordinates, we call the x coordinate h and the y coordinate k. Okay, Eliza, look through it. Can you see this okay?
Wait a second. H and K is kind of hard to like because there's like. Wait, let me see. Now you can kind of see.
Okay.
Yeah, I think you can
Thanks.
see.
All right, so that's an h and a k. So the coordinates of the center are called h and k. All right, and that'll be important when we write the equation of an ellipse. Okay. All right, now let's do this. I'm going to draw a dashed horizontal segment here that goes all the way across the ellipse in the longest way possible. Like that's the longest segment that I drew that goes across that passes through the center and comes out, goes in one side of the ellipse and comes out the other. All right, now that is called the major axis of the ellipse. Okay, so the major axis of an ellipse passes through the center and it goes across the ellipse in the longer way. Okay, it's farther from here to here than it is from here to down here. And at the end of each one of these, or sorry, what I should say is at each end of the major axis, we get something. We get okay. Now, Eliza, look at this. So this is called a focus. No, excuse me. Not called a focus. It's called a vertex. All right, so that's a vertex. At the other end, there's another vertex. What's the plural of the
vertices?
Perfect. Yeah. So, and nobody ever says vertexes. Okay, that's incorrect. But what people do sometimes say is they point at that point and they say, there's a vertice. Equally wrong. Okay, singular is vertex, the plural is vertices. All right, now the distance from the center to a vertex has a name. So the distance right here, okay, this from here to here, that is called the semi-major axis. Okay, half of it makes sense, the prefix semi. It's half the length of the major axis. And we have a letter that represents the length of the semi-major axis. And that letter is, and I'll put it right here, it's a lowercase a. Eliza, can I still see everything here?
See, the HK is still like in a thing.
In a dead zone?
Yeah, because it's like...
a glare zone or something?
Yes.
All right, well, kids, that right there says H and K. Eliza informs me it's difficult to see. How about the other stuff? Can you see everything else?
Yeah.
Wonderful, wonderful. Okay, now, let's go ahead and put a dashed horizontal segment that goes through the center, but this time the short way across the ellipse. Any guesses as to what we call that?
Minor.
Minor what?
Axis.
Minor axis. Yeah, good. Good context. Good use of context there. So this is called the minor axis. And then, of course, half of that is called the semi-minor axis. And it has a letter that always represents its length. The length of the semi-minor axis is represented with a lowercase b. All right, now we're not out of the woods just yet. Look, we can say that there are also vertices at either end of the minor axis, so we call those minor axis vertices. And if you're doing a problem and they say, name the vertices, okay, and they only give you 2 places, they're talking about the major axis vertices. But if they have space for 4 vertices, then they want all 4 of these, okay? All right, now, I'm going to grab a different tool here, a red marker, and
Fancy.
what?
Fancy.
Yeah. Okay, so I'm going to put 2 points, Eliza, to make sure the viewers can see.
Yeah, everything except part of center and HK.
Okay. So those 2 points play a vital role in the shape of the ellipse. And do you know what those are called?
No.
Okay. Each one of those, this is called a focus. And this one over here is also called a focus. So the plural of focus is F-O-C-I. Usually say that foci, although foci would be acceptable, I suppose. But foci. So here's a focus, here is a focus. So this ellipse has 2 foci. Now, the distance from a focus to the center. Well, it doesn't really have a name, but it has a letter associated with it, and it is lowercase c. Okay, so c is the distance from a center to a focus, and the foci are equidistant from the center, as you might suspect. Okay, now I think that is all of the pieces of an ellipse. And the very last thing I'd like to do on this slide, or on this isn't a slide, is it? On this whiteboard, is to write the equation in standard form of an ellipse. Now, first of all, I want you to think back for a second. You've all graphed lines for most of your lives. All right, and if somebody says, well, what's the equation of a line? Well, that has more than one answer, but a lot of you would default to your favorite form of a linear equation, right? Y equals mx plus b, okay, slope-intercept form. And that's fine. I mean, you can also write the equation of a line in standard form or in point-slope form, but this is fine. Now, the reason I bring this up is when somebody asks you what's the equation of an ellipse, the answer is probably going to be what I'm about to write right here, because this is in standard form, right? The equation I'm going to write here is the equation of an ellipse in standard form for the case where it has a horizontal major axis. Okay, so I'm going to write this. It's going to be x minus h squared over a squared plus, is this visible, Eliza?
Yes. I think.
Okay, so that's x minus, quantity x minus h, quantity squared, divided by a squared, plus quantity y minus k squared over b squared equals 1. Okay, so anytime we're going to write the equation of an ellipse in standard form, if it has a horizontal major axis, and as we'll find out in a little bit, the vertical major axis equation isn't really any different. It's going to look like this. Okay, now I want you to look at this for a second. You can see that there are several features of the ellipse embedded in the equation. Okay, just like with a slope-intercept form of a linear equation, features of the line are embedded in there. There's the slope, there's the y-intercept. Okay, down here you see an h and a k. Well, that will give you the coordinates of the center of an ellipse. And then, of course, a is the length of the semi-major axis. Well, the square of that is right there. B is the length of the semi-minor axis. The square of that is right there. So if I know the equation of an ellipse in standard form, I can pretty much graph it. Right now, I want to be clear here. If this is going to have a horizontal major axis, the number a has to be bigger than the number b. So this denominator.
Oh, jeez.
What's wrong?
Sorry, I was just trying to make it so you can see b squared better, because it's kind of hard to see b squared.
Right, so this denominator is going to be larger than this denominator if an ellipse has a horizontal major axis. As we'll find out, if that denominator, the denominator of the y term, is larger than the denominator of the x term, then you still have an ellipse, but it's going to have a vertical major axis. How are we doing on time?
20:03.
Oh gosh. Yeah, so I've exceeded the attention span of today's youth, I'm sure. But let's we'll go ahead and stop here. When we come back, we'll continue. Thanks. Have a good day.